Exercise 3 of Save the Earth. This will build on what you have done for Exercise 2. So we're starting here with some sample code from Exercise 2. Some of the details might be different depending on what numbers you found for various speeds and distances, what you decided to use for distance. But what you see here is some code. You can pull up your Exercise 2 and we will build on it starting after line 29. And we will look at and discuss a little bit some of the code that is given for Exercise 3 and what you need to put in, and also point out one thing that can happen. So in Exercise 2, you establish an initial distance between the asteroid and the Earth, and we want to keep track of that distance as the Earth and asteroid moves, and ultimately determine how close does the asteroid come to the Earth. So to keep track of that, something that I will call closest, short for closest distance, and on the left, this is creating a name, a space in memory, equal sign, and on the right, what are we putting there? And I won't type just a number, but whatever the distance d is, that was chosen for the initial distance. And this closest will change as the asteroid and the Earth are moving, and we will keep track of it in a way so that closest is always the smallest distance. Excuse me. Now we may want to track total time. I'll call that t, and we'll start with that equals 0. That won't be a big part of this exercise set, but something that will be is a different quantity, dt. T is the total time starting at 0, as if you started a timer. dt is going to be the little bit of time, in a sense, for each frame of the simulation. If you think of the simulation as a video of watching the asteroid and the Earth, the time between frames will be dt. And this is the time that will be used to determine how far the Earth and the asteroid go in each little bit of time dt, and then all of these will be added up. And I'm just going to put in 0.1. And again, this will be assumed to be seconds. Type in a comment to remember that. So the idea is that we're taking a video, a series of pictures of the Earth and the asteroid. The time between them is this amount dt, 0.1 seconds, and we want to see how the Earth and the asteroid move during that 0.1 seconds. Given where it was at the beginning of that time, where will it be at the end of that time? So the basic calculation is using the definition of velocity. And we're going to go through that calculation over and over for every frame, recalculate the new position of the Earth. So we will have what's called a loop. A loop is a set of repeated calculations, and there are 3 things that show that you're doing a loop, and you will need all 3. The first is some sort of word that will tell us either directly when the loop will stop, when we'll stop doing calculations, or say, well, keep doing the calculations as long as this is true. When we say while, we are saying keep doing these calculations over and over as long as some condition is true. So for instance, we could say we are going to track the asteroid until the asteroid is past the Earth the orbit of the Earth and has gone a distance past the orbit of the Earth equal to how far the moon is from the Earth. So, position of the asteroid is pos asteroid. And again, remember that capitals do mean something. In particular, we'll just track the y-coordinate of the asteroid. At the moment, it's just shooting down the y-axis, and when it reaches a certain value on the y-axis, then we'll stop and we'll keep going until then. So to get to that y value, we take pos asteroid dot y. That gives us the y component of the position. So we want to keep doing this as long as it has not reached the distance to the moon on the other side of the Earth's orbit, which will be in territory of negative y. So until that y-coordinate of the asteroid is negative d moon. That's one thing you need, is a condition that tells the repeated calculations, tell the loop, how long are you going to be doing this? When will you stop doing all these calculations? The next aspect you need is a colon. Reach the end of the line that tells you when the loop is going to keep going. Now if I hit enter to get a new line, you'll notice that the new line is automatically indented. And that's the third thing that lets you tell that you have a loop, and that is the lines that keep getting repeated are going to be indented. So as we go through these calculations, we want to update certain things. So time, for instance, we may want to keep track of what the total time is. Maybe later we'll make a graph. So this is an aspect where if you've not done computer programming before and you're used to equal signs in math, it's going to look a little weird. What do we want? We want to say that the time is changed to be the previous time plus the time from frame to frame. So in computers, the right side of the equal is something you're calculating. So this is saying take the number that is located in the location labeled t, add to it the number in the location dt. So calculate t plus dt at this moment, and then put that back into the place that's called t. So it's not just an equal sign, it's in a sense an assignment. It is saying calculate something on the right and set that to be the new value of the thing on the left. So this is updating time. We also want to update the position of the Earth. And that is going to come from the definition of velocity. Velocity is change of position. So the new position of the Earth, and we'll just call it pos Earth. There's no reason to have an old and a new name for it. Going to equal the old position of the Earth. So take the position of the Earth, add something to it, and say that is a new position of the Earth. And what do we add to it? By definition of velocity, it is vel Earth, the velocity vector of the Earth, times a little bit of time that has passed dt. Position and velocity are both vectors. Vector math says that the dt will be multiplied by all three components of the velocity vector, and ClosScript will take care of that for you automatically. It will automatically take care of the addition component by component on the right side, so you don't have to worry about that. Be very careful, though. This is a calculation for how the position of the Earth changes from one frame to the next, from one picture to the next, and the time between those is dt. You need to be a little careful. You don't want t here. We're not writing a total equation, trying to write the position at the end, just using the position at the very beginning, but just the beginning and end of a little bit of time dt. So this wants to be dt. In the exercise, you will add code here. It must be indented so that it is part of the loop. It is part of the calculation that keeps going over and over and over. And you will update the position of the asteroid. Now the given code shows you how, if you have the position of the asteroid and the position of the Earth, you go ahead and okay, let's be consistent about variables here. So I'm going to change this up here to pause asteroid. So we want to know where the asteroid is relative to the Earth and calculate that new distance between them so we can keep track of it. So using vector math, we want to know the difference between the position of the Earth and the position of the asteroid. We can call that relative position. Rel pause equals, and the order here doesn't really matter. If we type pause asteroid minus pause Earth, then that will give us where the asteroid is relative to the Earth. If you're on the Earth, where would you look to see the asteroid? And again, GlowScript will take care of the vector math of subtracting component by component. The distance between the two is the magnitude of this vector. Dist equals, and to calculate the magnitude of the vector, GlowScript has a function. It's called mag. And inside the parentheses, the argument of this function, you put the relative position, the vector whose magnitude you're trying to find. So dist will be the magnitude, the size of the relative position vector. That is at this moment of time. We want to keep track of when that distance is smallest. So this is a computer trick you can use. Go back to that variable called closest, and we'll say, okay, we want it to be the smallest, the minimum of these two quantities, whatever it was before, and whatever the distance is now. So we previously defined closest to be the distance at the beginning. Then when we have a new distance, if it's bigger, then closest will still be closest. But if the new dist is smaller, then closest will become dist. This is a way of keeping track of the smallest distance and calling it closest. And I'll do a couple lines and then do a backspace. No longer indented, so what I type now on line 46 will happen after the loop is done, after the asteroid has passed the proper position. And what do we want? We want to print, we want to show what is the closest approach. So closest approach, inside quotation marks, it's called a string. It will print out the words closest approach, a comma. What do we want to print? The number closest. Another comma, so we can make sure we add text that shows the units. And your part of the exercise will be adding the code on line 39 to update the position of the asteroid. Now, since that code is not there, the asteroid is not actually going to move yet until you put that code in, which means that this condition, while position of the asteroid y component, the y coordinate of the asteroid is bigger than minus d moon, well, the asteroid is not moving. It is always going to be at that initial position. So this condition would always be true. And When you have a loop condition that's always true, then you have what's called an infinite loop, and it will never finish. But I want to show you what will happen so that you can recognize when that sort of situation is occurring in GlowScript to help catch if you have accidentally caused this and happen. And it's a little different from what happens with most programming platforms or languages. Excuse me. In most platforms, if you did have this infinite loop down at the end of the program, then it would still go ahead and do all the stuff up here. It would print it out. And then would get into the loop and would be trapped in the loop, and you wouldn't see anything because we're not printing anything inside the loop. Nothing's printing until the end. So in most languages, we would see the velocity of the Earth, the position of the Earth, the asteroid velocity and position printed out, and then things would stop. But GlowScript is set up a little bit differently. If you have an infinite loop, in this case, first I'm getting an error because pause asked is not defined. That's because I changed names rather abruptly. It's telling me line 27. So I'll change this to asteroid. Excuse me. So you'll notice that it did do the printing, and then when it hit that line that it didn't understand, it stopped. But now everything is fixed. The only problem is the infinite loop. And now it's not even printing what it did before. It's trying its best to put the program together and put together an infinite loop, but nothing will happen until it's put together that infinite loop. And this is a sign of an infinite loop in GlowScript, is that you just keep seeing loading program and nothing happens. The rest of the program you don't see the output of because it's trying to put the whole program together. And unfortunately, you really have no option here except to, I could have clicked on close the window there, but basically you have to close the tab and go back. Clicking on edit will not get you back to the edit screen. It's just going to be locked up. So you just have to go back to GlowScript and find your way back to the program. And I will show you that what I'm saying is true by, in a sense, doing a fake thing. So I'm back to it. If I run it again, the same thing will happen. So I'm going to put a fake thing in here. I will just set the position of the asteroid. To have it on the y-axis. Just put it at the ending place, coming down the y-axis. So now once it's done that, the condition that the position of asteroid.y is bigger than minus d moon will no longer be true. Okay, apparently I didn't do that quite right. Okay, I misspelled asteroid here. I'm a little surprised it didn't complain about that. But the thing about computers is they do exactly what you tell them. And there you go. After I fixed that line, it put the asteroid beyond the position where it's running the loop, and then finished the loop and went to that last line. So we'll erase that. And your job will be to add this one line. And since you are not doing anything to change the path of the asteroid, you should find that the closest approach is very close to zero. How close to zero it will be will depend on exactly what you choose for this time between frames here. Choose that time to be bigger, your distance will be bigger. Because in a sense, you may have missed the actual closest approach. If you choose it to be smaller, the distance will be smaller because your frames are closer and you're becoming, in a sense, more precise. The trade-off is that when DT is smaller, the program will run a little slower. So it's something that you might have to play with a little. Okay, so that's exercise 3. The next one will be exercise 4, where we'll talk a little bit about the details of what you have to do when you are changing the velocity of the asteroid by exerting a force on it. And there's something you have to do in a particular order for it to work properly. Enjoy.